Welcome back to The Deep Dive, the show that cuts through the noise to get right to the core insights of complex research.
Great to be back.
We're deep into our Beyond Transformer series now, really exploring the cutting edge of sequence and language modeling architectures, trying to see what's pushing those boundaries.
Indeed. Last time we laid a lot of groundwork, didn't we?
We did. We got into the foundations of state-space models. We traced that line from Hippio with its, theoretical ideas about continuous time memory,
Right, that continuous summarization concept.
all the way to S4, its practical efficiency, its, frankly, impressive ability to handle really long sequences. We talked about how they build this kind of dynamic, almost brain-like memory.
Yeah, and we unpacked how models like S4 managed to get past some of those old limitations of RNNs by grounding their memory in those continuous time dynamics. It gave them a surprisingly robust and computationally pretty efficient way to process these exceptionally long sequences.
Right, tackling problems where
Yeah.
transformers, with their quadratic complexity, often just, well, they struggle.
Exactly.
Yeah, absolutely. And today, we're taking what feels like a really pivotal leap forward in that story.
Okay.
This is episode 3, and we're focusing squarely on Mamba 1.
Ah, Mamba, right.
This model, I think it's fair to say, represents the first major breakthrough in making SSMs not just, theoretically interesting, but truly fiercely competitive.
Head-to-head with transformers.
Head-to-head with transformers, specifically for the really demanding task of language modeling.
And what's so interesting here, I think, is that Mamba 1, it wasn't just a small step, an incremental improvement. It really introduced a fundamental paradigm shift in how SSMs are designed, how they actually work inside.
It reimagined their core, didn't it?
It absolutely did.
Exactly. So, our mission for this deep dive is to unpack that really revolutionary concept Mamba 1 brought in, what are known as selective SSMs.
The selective part is key.
It really is. We'll explain exactly how this innovation managed to overcome some pretty deep inherent limitations of those earlier, more rigid, linear time-invariant SSMs.
The ones we discussed last time, like S4.
Precisely. It's all about letting the core mechanics of the model adapt themselves based on the data that's coming in.
So dynamically choosing what to keep, what to ignore.
Exactly. What information to retain, what to let go.
Yeah.
And when you think about something as nuanced and, frankly, as variable in its information content as natural language,
Right.
that kind of adaptive intelligence isn't just a nice to have. It's absolutely crucial.
It becomes essential. And we should also definitely highlight one of Mamba 1's key advantages, especially when you get to inference time.
Yes, the practical side.
The constant state size. It sounds simple, maybe, but this design choice leads directly to linear time processing.
Oh, huge.
Huge. And critically remarkably efficient autoregressive generation. That's a game changer when you're thinking about deploying these massive language models that really define today's AI landscape.
Okay, let's do it. Let's unpack Mamba 1 and this power of selective state space models. Now, to really appreciate what Mamba 1 brought to the table, I think we first need to properly recall that dilemma, as you called it. The one that those early SSMs, specifically their linear time-invariant nature, kind of created when they were faced with complex, messy, real-world data.
Right. Let's set the stage again.
Yeah. As we talked about quite a bit last time, these linear time-invariant, or LTI, SSM S4 being the prime example we focused on.
A very capable example.
A very capable one, yes. They're fundamentally defined by their core state matrices, the A, B, and C matrices staying constant.
Fixed, unchanging across time.
Exactly, time-invariant throughout the entire sequence being processed. You can think of them almost like fixed filters.
That's a good analogy.
They apply the same set of operations, the exact same internal memory rules at every single time step. It doesn't matter what the input data actually is at that moment.
But, and it's really important to remember this, despite that fixed nature, these LTI SSMs were definitely not weak models.
Oh, not at all.
They showed some remarkable capabilities, especially on tasks that involve, very long-range dependencies, places where traditional RNNs or even standard transformers could often falter.
Right.
S4, for instance, it hit state-of-the-art results on really tough benchmarks like the long-range arena, the LRA.
Yeah, we talked about PathX.
Exactly, PathX. That involved sequences of, over 16,000 steps?
16,384, yeah. Insanely long.
And S4 managed to learn these complex, spatially consistent filters over these incredibly long inputs. It really showed its ability to abstract information across huge distances.
And it wasn't just synthetic stuff, right? Its success carried over. S4 did really well in practical things like raw speech classification.
That's right. It got, I think, 98.3% accuracy on data sets like SC10. And that was by directly processing 16,000 raw audio samples. No pre-processing needed, just raw waves.
And its efficiency, which we also covered last time, came largely from that equivalent convolutional view, right?
Yeah, yes. That was key for training. It allowed for significant parallelization, much faster computation during the training phase. Absolutely crucial if you want to scale these things up.
So you could train it much faster than a purely recurrent model.
Generally, yes. And the theory behind S4, it was deeply rooted in concepts like hippolegs.
Right, the Legendre polynomial projection?
Exactly. Projecting these continuous time inputs onto orthogonal polynomial bases, the intuition there is instead of trying to remember every single raw data point in some continuous stream.
Which is impossible.
Right, it's intractable. hippolegs gives you a way to continuously summarize the essence or the trends of that input history into a fixed-size state.
Like a running summary.
Precisely. Imagine creating this perpetually updating, incredibly compact summary of everything that's happened so far. It lets the model compress an entire history into a finite memory rather than needing to cache every single element like, say, a transformer does.
Okay, so on paper, these LTI SSMs look great. Powerful, efficient for long sequences, elegant theory.
They had a lot going for them.
Seemed like they had all the pieces for the next generation of sequence models. But here's where that dilemma really hits home.
Right.
Despite all these strengths, LTI SSMs face this really notable and maybe slightly perplexing challenge when you try to apply them to what researchers call information-dense data such as language.
And that really begs the question, why? Why would a model that's so good at long-range dependencies and efficient memory struggle specifically with something like language?
It seems counterintuitive at first.
It does. But the core issue, it really lies in their time-invariant nature. That leads to this fundamental problem of uniformity.
Uniformity. Explain that a bit more.
Well, language, unlike maybe fixed-rate signals like raw audio or certain types of vision data, carries information at incredibly variable rates.
Okay.
Think about just reading a sentence. A common function word like the or a, it might convey very little new or surprising information. It's almost like grammatical glue.
Predictable. Low entropy.
Exactly. But then the moment you hit the beginning of a new, complex, maybe unpredictable word, especially a proper noun or a very specific technical term, that single token suddenly demands a dramatically higher level of, let's say, attention or memory update?
Right, it carries much more meaning, more surprise.
Precisely. An LTI SSM, because its matrices A, B, and C are constant, static, it treats every single part of that sequence with the same uniform level of importance or compression.
It applies the same fixed filter.
The same memory rules, whether it's processing a highly predictable low-entropy word like the, or a novel high-entropy piece of information like a new name.
And that's just not optimal, is it? For the dynamic, often sparse, very unpredictable flow of information you get in natural language.
It's a mismatch. The model fundamentally cannot adapt its internal memory based on the changing information content of the input. It processes that low-entropy function word with the exact same fixed mechanism as a high-entropy, semantically rich noun.
Which feels inefficient at best.
And limiting at worst. If you think about the bigger picture, this uniform processing means LTI SSMs inherently lack the ability to selectively retain or discard information based on its immediate relevance or novelty.
Okay.
Imagine like a student taking notes in a lecture. An LTI model would be like highlighting every single word with the same bright yellow highlighter, regardless of whether it's a keyword or just filler.
Which makes the highlighting useless.
Pretty much. It leads to wasted memory capacity because you're spending resources on trivial details, and it reduces your ability to capture the nuanced, shifting meaning within a sentence or discourse. This fundamental limitation really prevented them from efficiently modeling that intricate, varied information flow that's just the hallmark of linguistic data.
And this finally brings us directly to the Mamba 1 breakthrough.
Yes.
The introduction of selectivity. This concept, it really did change the game for state space models, especially in the realm of language modeling.
It was a pivotal moment.
The work by Gu and Dao in 2023, it introduced this, well, groundbreaking new paradigm, selective SSMs. sometimes also called time-varying structured SSMs.
Time varying, that's another good way to put it.
And it marked a profound, really fundamental departure from those LTI predecessors. It tackled that core uniformity problem head-on.
And what's truly revolutionary here, the absolute core innovation, is how it did that. Those transition matrices A, B, and C, the ones that define how the internal state evolves and how inputs get incorporated.
The heart of the SSM.
Exactly. They are no longer fixed. Crucially, they are now allowed to depend on the input and vary through time.
So they change at each step.
They can, yes. This dynamic adaptation, this ability for the model to change its own internal mechanisms on the fly based purely on the incoming data, that is the essence of selectivity.
Okay.
So unlike the constant matrices of LTI SSMs, Mamba's matrices are often computed for each step derived directly or indirectly from the current input token. This enables a vastly more flexible and, well, intelligent interaction with the sequence.
Right. So what does this actually mean for tackling those language modeling challenges we just discussed?
It means Mamba 1 gains this incredible, almost intuitive-seeming ability for intelligent information management.
Okay.
By making those transition matrices beta-dependent, Mamba 1 gets the power to, and this is their phrasing, attend on or ignore inputs at every time step.
Now, attend on there doesn't mean transformer attention, right?
No, absolutely not. It's a different mechanism. Think of it more like an internal adaptive gating mechanism. It empowers the model to intelligently choose what information to remember as it moves through the sequence.
Like that adaptive filter you mentioned.
Exactly. A finely tuned, highly adaptive filter, dynamically deciding what actually merits retention in its compact state memory and what can be safely disregarded, much like, an efficient human memory system filters out noise.
That makes sense. And this adaptive filtering, it must be critical for modalities like language, where, as we said, the information density just fluctuates wildly.
Absolutely critical. Let's maybe walk through a quick linguistic example just to make it concrete.
Yeah, good idea.
Imagine the model is processing a fairly common, predictable phrase like, the cat sat on the mat.
Okay.
An LTI model, remember, would process the twice using the exact same fixed mechanism. But a selective SSM, like Mamba, might dynamically adjust its B and C matrices when it sees the first the.
How so?
Well, maybe the input the signals to the model, okay, this is a low information, very common word, minimal update needed to memory state.
Right, don't waste resources.
Exactly. Then when it hits cat, the model might drastically change those matrices based on that input. It signals, cat, this is a more salient noun, probably important, requires a more significant update to my internal state.
Okay, I see.
And then further along, if it encounters, say, a complex, rare, proper noun or a completely new technical concept it hasn't seen much before.
A high entropy token.
Right. The matrices would adapt again, maybe even more dramatically, allowing the model to devote more of its internal resources, more of its state capacity, to capturing that specific, surprising unit of meaning.
So it adjusts its memory and processing based on these linguistic surprises, instead of just treating everything the same way.
Precisely. That's the core benefit of selectivity for language.
And the empirical results, they actually showed this played out.
They really did. The paper showed that selective SSMs perform much better than LTI SSMs on information-dense data such as language.
Okay.
And interestingly, this advantage became even more pronounced, especially as its state size, n, increases.
So the size of that internal memory matters even more here.
Yes, because a larger N in a selective SSM doesn't just mean more general memory capacity. It means more room to selectively abstract and retain diverse, complex information.
So it's not just a bigger memory, it's a smarter memory.
That's a great way to put it. It's like having a bigger, more sophisticated filing system where the system itself decides which documents need detailed folders and which can be summarized briefly. It allows for more information capacity because it's more selective about the content.
And this selective mechanism, how does it compare conceptually to how transformers handle information? Because that's the dominant paradigm people know.
That's a really important distinction to make, especially for listeners familiar with transformers. Transformers, by their very design, essentially cache everything.
The whole history.
Pretty much every element of their history in the form of key-value pairs. Then they perform attention over this potentially massive cache. It acts somewhat like an incredibly efficient but fundamentally unselective database lookup.
Okay.
SSMs, as we've discussed, are different. They compress their entire history into a finite-sized state. It's more akin, perhaps, to how a biological brain might process information in real time, constantly evolving its internal representation, its memory, rather than storing every raw input perfectly.
Right, a continuous update.
Mamba 1 takes that brain-like analogy maybe a step further by making the compression itself dynamic and intelligent. It focuses the compression effort only on what truly seems to matter based on the input. It's a fundamental difference in how they approach memory and context compared to transformers.
Okay, that distinction is clear. Let's maybe shift gears slightly and unpack some of Mamba 1's specific architectural choices and, crucially, its inference characteristics. Because there are some really significant differences here, especially if you compare it to S4 or Transformer.
Absolutely. There are some key design points.
One really crucial difference, maybe sometimes overlooked but quite important for understanding its behavior, is that Mamba 1 was inherently computed in recurrent instead of convolutional mode for its training.
Right. That's a big difference from S4's convolutional option.
It is. It meant its forward pass during training was fundamentally sequential, token after token, one by one, rather than processing big parallel blocks like S4 could do in its convolutional form.
Which impacts training speed and parallelization.
Yes, exactly. S4's convolutional approach allowed for inherent parallelizability, processing large chunks of data simultaneously, which generally leads to faster training on parallel hardware, like GPUs.
Yeah, to use an analogy, think of maybe a factory assembly line. S4, when trained convolutionally, could be like having many parallel workers, each assembling a small batch of products at the same time. Then you quickly stitch the results together at the end, makes training very fast.
Yep.
Mamba 1, in its recurrent training mode, was more like a single, highly skilled worker processing one item completely from start to finish before moving to the next. Still effective, but the overall throughput, especially on highly parallel hardware, wasn't quite as optimized as S4's convolutional path.
Got it. So training might have been less parallelized than S4 convolutional.
Yeah.
But despite that sequential nature during training, Mamba 1 really shines during inference.
Yes, when you're actually using the model.
When you're generating text, for example.
Mm.
Mamba 1 maintains a constant state size during inference.
This is the critical point.
It's a critical, absolutely enormous advantage for autoregressive generation. That's the process, of generating new tokens one by one, word by word, like a chatbot does, or when completing a sentence.
Right.
This constant state size leads directly to linear time processing.
Meaning the compute cost scaled only with the length of the sequence, not quadratically.
Exactly, not length squared. And this enables efficient autoregressive generation. Each new token you generate costs the same amount computationally, regardless of how long the sequence you've already generated is.
And that constant state size during inference, it's truly a game changer for actually deploying large language models in the real world.
Why is it such a big deal practically?
Think about it. A standard transformer's attention mechanism, it scales quadratically with sequence length, even during inference.
Right. The key value cache grows.
Exactly. So if your generated text doubles in length, the computational cost to generate just the next single token quadruples, or worse, depending on the implementation. This becomes prohibitively expensive very quickly for long outputs.
You hit a wall.
You hit a wall. Mamba 1, however, just needs to update its fixed size state. The cost to generate the 1,000th token is essentially the same as the cost for the 10th token.
Wow.
This translates directly into lower compute requirements, faster response times for users interacting with the model, and significantly better scalability for deploying these truly massive language models that need to handle long contexts efficiently without breaking the bank.
That linear scaling for inference is a massive practical advantage then.
Absolutely massive.
Okay. And there were a couple of other key architectural points mentioned in the original paper too, right?
Yes, a few more details. The initial Mamba model was specifically unidirectional, meaning it processed sequences strictly in a forward causal direction, predicting the next token based only on the tokens that came before it.
Which makes sense for standard language generation.
It's the natural choice for autoregressive language modeling, yes, but it's also worth noting that this design choice strategically paved the way for later innovations.
Bidirectional models.
Exactly, like bidirectional extensions such as Hydra, which we'll definitely cover in a future deep dive. Hydra was designed specifically for non-causal tasks, like masked language modeling, where the model needs information from both the past and the future context to make predictions. Mamba's initial focus on unidirectional flow made extending it conceptually cleaner later on.
Interesting. And there was also mention of sequential projections.
That's right. Mamba also used something called sequential projections within its architecture.
What exactly are those?
Well, the original Mamba 1 paper didn't go into exhaustive low-level detail on them, but they were an integral part of its internal structure. Conceptually, you can think of them as specialized linear transformations applied to the input at each step.
Before it affects the state.
Generally, yes, before that input influences the dynamic A, B, C transition matrices, these projections essentially help to shape or transform the incoming data into a format that's most effective for the selective SSM mechanism to then operate on.
Kind of like pre-processing the input for the core mechanism.
That's a reasonable way to think about it. And it's also noteworthy that these specific sequential projections were actually modified in later work, particularly in Mamba 2.
Why change them?
To enhance properties like tensor parallelism, which, for our audience, basically means making it easier to distribute the large matrix computations involved across multiple GPU accelerators efficiently. These modifications were crucial for tackling some of Mamba 1's hardware efficiency challenges we'll get to shortly.
Okay, that makes sense. Improving the hardware fit. Let's move on then to the empirical performance of Mamba 1. How well did it actually do? And also, let's touch on those initial hardware considerations you just alluded to.
Right. The results were quite striking. The original Mamba models from Guo and Dao's 2023 paper, they showed genuinely impressive performance right out of the gate.
Especially compared to transformers.
Exactly. At what they called small to moderate scale, Mamba models matched or beat transformers on language modeling.
Matched or beat, that's huge.
It was huge, a really significant achievement, arguably groundbreaking at the time, given how dominant transformers had been, and frankly still are, in language modeling. For a fundamentally different architecture to go head-to-head with the king and actually win, even at those smaller scales, was a powerful validation of the whole selective SSM concept.
Wow. Okay. And did they test it on specific tasks to probe its abilities?
Yes, they did. The paper meticulously showcased Mamba's capabilities on specific synthetic benchmarks designed explicitly to test a model's memory and recall abilities.
Things like?
Things like selective copying and induction heads. These are often characterized as simpler, perhaps associative recall tasks. Meaning the model has to learn to associate specific inputs, like a key, with specific outputs, like a value, and then accurately retrieve that value much later in the sequence, often after seeing many distracting items in between.
So testing memory over long distances.
Precisely. They're not trivial tests at all. They directly assess the model's capacity for handling long-range dependencies and performing intelligent memorization and recall.
And they also use something called MQAR tasks.
Yes, further validation on related tasks called multi-query associative recall, or MQAR. And these MQAR results really underscore the importance of that state size n for Mamba's performance.
How so?
The researchers systematically showed that as they increased the state size n, say, going from a fairly small n16 up to n64, and then up again to a much larger n256, the performance on these recall tests consistently improved.
Better recall with bigger state.
Consistently better. It directly demonstrated that larger states enabled the model to memorize a greater number of these key value associations accurately. This is a direct consequence of the model having more internal capacity combined with its enhanced selectivity. It implies that with more internal slots or dimensions in its state, Mamba could selectively capture, retain, and distinguish between more complex, fine-grained pieces of information.
Okay, so strong modeling performance, especially as the state size grew.
Right.
But you mentioned hardware challenges. Let's get into that.
Right. This is where the initial excitement met some practical realities. Despite its powerful modeling capabilities and those promising empirical results, Mamba 1 faced a pretty significant hurdle: practical hardware efficiency.
It wasn't as fast as hoped.
It quickly became clear that the model required a careful hardware-aware implementation to be efficient. It wasn't just a matter of coding up the math, you needed specialized optimizations.
Not plug and play.
Definitely not plug and play.
Huh?
It indicated that actually achieving its impressive performance in practice, particularly as you tried to scale the model up, wasn't straightforward. It demanded highly optimized custom kernels.
Meaning specialized low-level code.
Exactly. Code written specifically to manipulate the GPU hardware efficiently for Mamba's unique operations, or at least very meticulous software engineering, to unlock its full speed potential. Without those kinds of bespoke optimizations, Mamba 1's raw computational throughput tended to lag behind more established architectures.
And crucially, even with those painstaking optimizations,
Yes, even when implemented carefully, Mamba 1 was still less efficient than hardware-friendly models such as CNNs and transformers,
Why? What was the fundamental reason?
because it did not leverage matrix multiplication units, which modern accelerators such as GPUs and TPUs are specialized for.
Ah, the tensor cores.
Exactly. This is a fundamental bedrock point that explains a lot about where the research went next. Modern GPUs and TPUs, they're incredible pieces of engineering specifically designed for massive parallel computations. Their specialized tensor cores, or matrix multiplication units, are unbelievably efficient at performing the large-scale matrix multiplications that are the absolute bread and butter of transformer operations.
Transformers are basically built around matrix multiplies.
Almost entirely. They align perfectly with what the hardware is best at. Mamba 1's computational patterns, however, were different. They rely more heavily on things like element-wise operations, scans, recurrent computations.
Different kinds of math.
Different kinds of math that, while theoretically efficient in terms of total operations, didn't map as cleanly onto these specialized tensor cores. It's like having this super fast, custom-built highway designed specifically for massive semi-trucks, matrix multiplies. And Mamba 1, while being a powerful vehicle in its own right, was built more like a nimble, custom-engineered sports car.
Fast, but not using the highway optimally.
Exactly. It was fast, potentially very capable, but it wasn't designed from the ground up to maximize throughput on that specific hardware architecture. This meant Mamba 1 struggled to fully exploit the raw power of modern GPU tensor cores, leading to practical bottlenecks, especially in large-scale training and deployment scenarios compared to transformers.
And this limitation, this hardware mismatch, became a major driving force for what came next.
Absolutely. It became a pivotal, defining motivation for the next wave of developments in the SSM landscape. Mamba 1 unequivocally proved the conceptual power of selective SSMs. It showed they could tackle language modeling effectively, but deploying them at very large scales efficiently, that necessitated a fundamental rethinking of the computational primitives to better align with modern hardware.
Which leads directly into things like Mamba 2.
Precisely. This challenge directly led to the innovations we're going to explore in our very next deep dive, particularly Mamba 2, which specifically aimed to bridge that hardware-software gap to get the best of both worlds, the modeling power of selectivity and the hardware efficiency of architectures like transformers.
Okay, fascinating. So as we wrap up this deep dive on Mamba 1, it feels abundantly clear that it wasn't just, another sequence model dropped into the mix.
Not at all.
It was a truly pivotal conceptual leap, a paradigm shift, as you said earlier.
Yeah.
By introducing this core idea of selective SSMs, it fundamentally changed how we could approach memory and information processing in neural networks for sequential data.
It really did. It proved that SSMs could do two critical things simultaneously: handle incredibly long contexts efficiently, keeping that linear time inference cost,
The constant state size advantage.
and adapt their internal mechanisms dynamically based on the actual information they encounter in the input stream.
Which is a stark contrast, really, to both ends of the spectrum we had before.
Exactly. It contrasts sharply with the rigid, uniform compression of the older LTI SSMs, which just couldn't adapt to variable information rates effectively.
Yeah.
And it also contrasts with the comprehensive, but ultimately unselective caching mechanism of standard transformers, which basically just try to store everything they've seen.
Mamba found a middle ground, an adaptive ground.
It offered a powerful new primitive for sequence modeling, one that allows models to be genuinely intelligent about what they choose to remember, rather than just uniformly compressing everything or trying to store everything. This dynamic adaptation, this intelligent filtering, it's a profound advancement, especially when you're dealing with variable rate, information-dense data like natural language, which is inherently messy, unpredictable, and full of surprises.
So while Mamba 1 definitely showcased this incredible modeling ability, especially beating transformers at smaller scales for language,
Which was huge.
its initial hardware efficiency challenges clearly highlighted concrete areas where improvement was needed.
Yes, the path forward was clear.
Yet, crucially, it laid that essential groundwork. The foundational concepts were proven. It guided the development of the more optimized, more versatile SSM architectures that followed.
Architectures that are now really starting to reshape the landscape of efficient, long-context AI. And as we've hinted, we'll definitely be diving into those exciting developments, particularly Mamba 2 and Hydra, in our upcoming deep dives.
Can't wait for those. Okay, this brings us, as always, to a final provocative thought for you, our listeners, to maybe mull over.
What are the broader implications, really, of a model that can intelligently choose what to remember in this never-ending stream of information we live in?
Yeah, think about how our own biological brains work. We constantly filter, we prioritize information. We have to discard irrelevant noise just to function, to focus on what's salient.
How might this kind of selective attention built into an AI model lead to systems that are more robust, maybe more efficient, and ultimately perhaps even more intelligent in a practical sense? Especially when they're processing the messy, real-world data that fills our lives, data with highly variable information densities.
This adaptive context management, it feels like more than just a technical trick.
It feels like a truly powerful, primitive, maybe even a necessary one in the ongoing evolution of sequence modeling. It pushes us closer, perhaps, to systems that can learn and adapt with something resembling a more human-like discernment.
That adaptive context management, the ability to dynamically prioritize information, a powerful primitive indeed, with implications far beyond just language modeling. We've certainly covered a lot of ground today unpacking Mamba 1.
We have. It's a fascinating model.
Join us next time as we continue our journey beyond transformers and look at how Mamba evolved.